Hello, everyone, and welcome back. Today is day three of our work finding volumes of three-dimensional objects. And today is day two talking about volumes of solids of revolution, which we began to talk about yesterday. Today, we are going to introduce an alternative method of finding the volumes that is based on an alternative way of slicing your object. Yesterday, we focused on slicing the object so that either disks or rings were formed so that we could find the area of those disks or of those rings by using the geometric formula for the area of a circle. Today, we are going to focus on slicing our object differently, not slicing it into disks, but slicing it into cylinders. And to demonstrate a situation where I would definitely want to think about slicing my object differently than we did yesterday, let's consider the following exercise. I have a three-dimensional object, and this object is formed by taking the region bounded by this exponential function y equals 0, x equals 0, and x equals 1, and spinning this region around the y-axis. Let's find the object's volume. So here I am on Desmos, and I have graphed the four functions which form the borders of this region. So here is x equals 0, here is x equals 1, here is y equals 0, and here equals y is that exponential function. And let's think about what would be entailed if I took this region and I spun it around the y-axis and I tried to make sense of the areas of the slices cut perpendicular to that y-axis. Now, if I spin this object around the y-axis, and if I decided to try and use the same technique that we introduced yesterday, I would go into this object and I would make a slice in the object that is perpendicular to that y-axis. So for an example of a slice that I might take toward the bottom of the object, I might take a slice that looks like this, and then I would spin that slice around the y-axis, and that spinning would form a circle. So the area at this particular y value would be found by taking pi times the radius squared of this slice down here at the bottom. And then I would have to do some work to find out the radius of that slice at that generic y value. Now, I can see that for slices that are down here toward the bottom of the object, the radius is actually always fixed. If I take any slice down here toward the bottom of the object, the radius of that slice is always going to be equal to exactly 1 unit. The radius equals 1 down here. That's because for all of these slices taken toward the bottom of the region, the slice extends from the center of the picture, the central axis, over to this value here of x equals 1. And so the length of that segment would be the distance between 1 and 0. And so all of those slices would have a radius of 1 unit precisely. But something changes dramatically as soon as we hit this corner right here. As soon as we hit this corner where the exponential part of the function takes over, the nature of my slices has changed. Because now, if I slice into the object, the slices are not even really the same shape that they used to be. Because when I take a slice up here, perpendicular to the y-axis, and I spin it around the y-axis, I see what's being formed in this case is a ring. And because what is being formed up here is a ring, the area of a slice taken at that y value would have to be formed by doing the area of the outer disk, pi times the outer radius squared, minus pi times the inner radius squared. And so not only And so we can see that sort of halfway through the region, the nature of the area function changes dramatically. Because of that, this a of y function would be piecewise. It would have one formula on the bottom of the region where the y values are small, and it would have a totally different formula on the top of the region where the y values are large. And because a of y is piecewise, if you were going to try and find the volume by integrating a of y, you would need to find the area function twice. You would need to find the area function for the bottom of the region. We would need to find the area function again for the top of the region. And then we would need to use pit stop rule to split this integral into two pieces and integrate each of those pieces separately. So altogether, this is a ton of work, right? It's a ton of work because, I mean, finding a single area function is already really difficult, isn't it? But finding two area functions is even harder than that. And then to have to take two integrals, both of which, might be hard as well, that's a lot of work. And so that is why, for a situation like this one, I'm very strongly motivated to try and find the volume of the object a different way, using a different technique than what we used last time. Now, the thing that I'm going to do differently is that instead of cutting the slices in this particular way, perpendicular to the y-axis, I'm going to try and cut the slices in the opposite direction, and I'm going to try and cut a slice into this region that's vertical. I'm going to cut a slice that is parallel to the axis around which I am spinning this object. And let's see what happens geometrically when those slices are spun around the y-axis. Just to show you pictorially what I mean, here I have recreated the region in question, which is being spun around the y-axis. And this time I'm going to make cuts that are parallel to the axis around which I'm spinning. I'm spinning around the vertical axis, so I'm going to try and cut vertically into the region. And then I'm going to think about what kind of shape is formed when that particular slice is spun around the region. Well, if I take a vertical bar like this and spin it around the y-axis, it looks like the sort of geometric shape that's being formed like that is a cylinder. So if I want to find the area of this slice that was formed by taking a vertical cut into the region and spinning that around the y-axis, what I should be able to use is the cylinder area formula, which if you don't remember, can be found by taking 2 times pi, multiplying that by the radius of the circle, which is extending from the center to the edge like this, and multiplying that by the height of the height of the cylinder being this distance right here from the top of the cylinder to the bottom. If I can find a function which I give it the x value of whatever slice I've decided to take, and the function gives back to me the area of the cylinder corresponding to that slice, if I can find that function, that area function, then all I have to do is integrate that area over all the relevant x values, and the integral of the areas of those slices will give me the volume of the object in question. So once again, for clarity's sake, I wanted to go to GeoGebra to show you a little bit of what is going on. So here in blue is the region that we are given to spin around the y-axis. This is a slightly simplified version of this region because we have a curved top from the exponential function, and I just for simplicity's sake have treated the top of the region as a straight line. And what I have drawn here in black is the cut that we have made vertically, this time um, parallel to the axis around which this object is being spun. Now, as we spin that vertical cut around the y-axis, the shape that is formed by that line segment is a cylinder. We can see it here as I drag the object around the y-axis and spin it around the y-axis. We can see that that vertical slice is tracing out the shape of the cylinder. So this is what is going on visually, represented on the computer for a little bit of extra visual clarity. Now that we have done that, let's go ahead and try and figure out what function we could use for the area of these cylinder-shaped slices, and specifically what would form the radius and what would form the height of a cylinder taken at a random x value between, in our case, x equals 0 and x equals 1. Now, the picture may give us some nice information here. The radius of the cylinder is stretching all the way from the central axis to the x-coordinate where the cut was made. So it looks like the radius of the cylinder is an exact match to the x-coordinate of the cut in this picture. Now, in terms of the height of the height of the cylinder looks like it is stretching from y equals 0 at the bottom to y equals our exponential function at the top. So it looks like the height of the cylinder is an exact match to the y coordinate of that upper corner here. And expressed as a function of x, this would be e to the x squared. The formula in terms of x for the height along that exponential curve at the top of the cylinder. So if I plug those values into our cylinder area formula, I get that the area as a function of the x-coordinate where the slice was made is given by the product 2 times pi times x times e to the x squared. And then if I wanted to find the volume from that, all I would have to do is integrate that area formula from the smallest x value, x equals 0, to the largest x value, x equals 1, for the region. Now, the integral contains a product of x times e to the x squared. And because I have a product where I have a function and I have the derivative of that same function present in the product, I think that this is a great opportunity to use method of substitution. For example, with u equals x squared, giving me du equals 2x dx, or in other words, 1 over 2x du, replacing dx. If I put that information into the integrand, I get 2 pi x e to the power u times 1 over 2x du. And that has worked out very nicely because this 2x cancels this 2x, and all I'm left with is the integral of pi e to the u. Now the antiderivative of e to the u times a constant is just e to the u again. And if I put back the original meaning of u into this position, I get pi e to the x squared plus c. And from that indefinite integral, I can use this one particular antiderivative to help me to find the definite integral that I am looking for. All I have to do is plug in the two limits of integration and subtract, and I get this result. Pi times e minus pi is the exact volume of the object that is indicated by this exercise. So we get a different method of finding volumes if you slice your region a different way. If you slice the region parallel to the axis that you're spinning around, then those slices will give rise to cylinder shapes. Let me give you another example of a situation where I think I would be highly motivated to make cuts that formed cylindrical shapes as opposed to making cuts that formed circle shapes. And so here we have a three-dimensional object formed by taking this region bounded by this parabola at the top and by y equals 0 at the bottom, and spinning that region around the y-axis. Let's try and find the volume of this object. So once again, the first thing I'm going to do is I'm going to draw the region, and I'm going to draw at least one slice from the object. So here's our x-axis, here's our y-axis, and here is our parabola shifted 2 units to the right and 1 unit up. So I think it looks a little bit like this. And then it's also bounded, the region is also bounded on the bottom by y equals 0. So our region looks a little bit like this wing shape. And then we are spinning that region around the y-axis, and we're going to try and find the volume of the shape that results, the object that results. Now, there are a couple of different reasons why I would not want to make a cut in the horizontal direction in this situation. If I tried to make a cut in the horizontal direction in this situation, so that spinning that cut around the y-axis created a ring shape, I think it would be quite hard for me to find a formula which gives me the inner and the outer radius of this circle. It looks like the inner radius is somehow living on the left half of this parabola, and the outer radius is somehow living on the right half of this parabola. And it might be quite time consuming and labor intensive to find the formulas for the left half and the right half of the parabola in this picture. So instead, I'm going to try and take this same image, and I'm going to think about making the cuts and slices into my object in the opposite direction, not horizontally, but instead vertically. And let's see if slicing things vertically creates a slightly easier geometric problem. So in this situation, I will be slicing vertically into the object at different x values. And if I spin that vertical slice around the y-axis, then once again I have a cylinder formed. So the area of this slice could be found using the area formula for a cylinder, 2 pi times the radius times the height. So I just need to figure out what would the radius of the cylinder be and what would the height of the cylinder be, both in terms of x, for a slice taken at this random x value. Well, looking at the picture, once again, our radius appears to be an exact match to our x-coordinate of the slice, because that radius is extending from this central axis at x equals 0 out to the x-coordinate of the slice. So again, the radius of the slice is x in this particular example. And once again, we see that the height of this cylinder is extending from this base of the region down here at y equals 0 up to the top of the region, which is formed by our parabola, y equals this guy right here. So it looks like the height is an exact match to our y coordinate in this case, which as a function of x would be x minus 2 squared plus 1. So I'm going to use this for the radius, x, and I'm going to use this for the height, x minus 2 squared plus 1, and putting those together, I get an area formula of 2 pi x times the quantity, x minus 2 squared plus 1. And integrating this area formula from our first value of x to our final value of x is what's going to give me the volume of the object in question. Okay, let me simplify this area function first of all. And now I will integrate that area function from the smallest x value in the region to the largest x value in the region. Oops, I just realized I had an error in the problem statement compared to my drawing. I was thinking that the problem statement had a y value of negative x minus 2 squared plus 1. I'm going to go ahead and fix this problem statement so that the parabola is upside down, because the parabola has to be upside down in order for it to actually bound a finite region. And let's see, that would show up as a minus sign here. That would show up as a minus sign here. That would show up as a minus on the x squared, a plus on the 4x, and then this would be negative 4 plus 1, so that would be a minus 3 in the back. And then after distribution, we would get a negative 2 pi x cubed. We would get a positive 4 pi x squared, and we would get a negative 6 pi x in the back. So hopefully that fixes things. Okay, having caught that, let me go back to Desmos and fix the graph as well. Here is the graph of our parabola, and here is the portion of the parabola that is sort of being cut off by the y equals 0 curve on the bottom. And so from this picture, I can see that the x values that are relevant for my integral are the ones between 1 and 3, because those are the final x values where the parabola lives above this y equals 0 line. So those will form my limits of integration, x equals 1 and x equals 3. Once that is done, the only thing that's left to do is to go ahead and calculate the actual value of this definite integral, and that will happen in the usual way, using, in this case, power rule to find an antiderivative, plugging in those lower and upper limits. Okay, and so this result, simplified if you care to simplify it, this would be the exact value of the object which is being described in this problem statement. Okay, to summarize, when we're finding the volume of a solid of revolution, which is an object formed by spinning a region around an axis, there are two main ways to go about it. You can either slice the object perpendicular to the axis around which you're spinning, or you can slice the object parallel to the axis around which you are spinning. Depending on which you decide to do, the cross-section corresponding to that slice is either going to be shaped like a disc or a ring, or the slice is going to be shaped like a cylinder. And therefore, you can use the area formula, either the formula for a disc or the formula for a ring, or the formula for a cylinder, to help you to find the area of the slice that you just made, an area function for the slices in your object. And once you have found the area formula, then all you have to do is integrate that area formula, and that will give you the volume of the object.